We can kind of view chemistry in two different realms: the micro world, which consists of atoms and molecules, or particles of things, or the macro world, which is stuff we can actually see, which we might call, we see that and we could weigh it as grams. So the atomic mass is the mass of an atom in atomic mass units, or AMU. And by definition, one atom of carbon-12 weighs 12 AMUs. Alright, so which carbon is it? Carbon has several isotopes, but it's carbon-12. On this scale, hydrogen weighs 1.008, and oxygen weighs 16 AMUs as well. But we set everything as a reference to carbon, probably because it's one of the most abundant elements on the Earth. Natural lithium is 7.42% lithium-6, and it's 92.58% lithium-7. In your next podcast, you're going to see how these percentages come about. Alright, it's with a special machine. And we'll kind of look at that more in our next podcast. But for now, just how do we solve these problems? Well, our percentages, we're going to change to a decimal number. So 7.42% turns into 0.0742. And we're going to multiply that by our mass, which in this case is 6.015 AMUs. And then we're going to add that to our other percentage. Alright, so we're going to change our percentage to a decimal, so 0.9258, times our other mass, which in this case is 7.016 AMUs. And when we add those together, we get 6.941 AMU. And where is this number, or where do we find it important? Well, it is the number that's on the periodic table. So for lithium, we have 6.941. It's the average atomic mass, and it's not just an average. We don't take 6 divided by 7 and get 6.5, but it's a weighted average. And for every element, we have weighted averages for boron, for silicon, for cobalt, so on and so forth. Alright, so the decimal numbers in the periodic table are atomic masses. Alright, the other thing we're basically looking at is the idea of a mole. Alright, we have various words in the English language that tell us numbers: dozens, 12, pairs, 2. A gross is 144. You might buy a dozen eggs. Pencils are sold in the gross. A fortnight is 2 weeks. 4 and 7 years ago, scores are 20 years. And then a ream of paper is 500 sheets. So again, in English we have several words that have quantities, values. The mole is another one of these words. It is actually the metric unit for quantity, just like meter is the metric unit for length, or kilogram is for mass. Mole is quantity, and it's the amount of substance that contains as many particles as there are atoms in 12 grams of carbon-12. Okay, and what is that value? It is 6.02 times 10 to the 23rd. You can ignore those other digits that come after the 6.02. And then the Na is, that A stands for Avogadro, and this number is named after Avogadro. He was a scientist which primarily worked with gases and determined this number from gas samples. Alright, so a molar mass is the mass of a mole of anything in grams. So it could be eggs, it could be shoes, it could be marbles, but really we're concerned about atoms. But again, a molar mass is the mass of anything in grams. Most of these masses would be unbelievably huge unless we're talking about atoms. But if we're talking about atoms, 1 mole of carbon atoms, which means 6.02 times 10 to the 23rd atoms, which is a lot of atoms, weighs 12 grams, which is not much at all. Again, a single carbon atom weighs 12 AMUs. And notice the difference between 12 atoms and a mole is just simply gram and AMU. And this holds true for any other element on the periodic table. So really the periodic table tells us atomic masses, which are AMUs. Oftentimes I will verbally say molar mass, but what's the difference between these two things? Only their unit. Numerically they are identical to each other. So again, periodic table tells us atomic masses, but really I will say molar masses almost every time. I forgot to delete this. Oh yeah, here we go. Why I had this slide up is moles represent two things then. We might do a little mole map, but moles relate to particles. Alright, and particles can be atoms, they can be molecules, they can be formula units. We'll talk about that in the next few slides. But when we relate moles and particles, 1 mole always equals 6.02 times 10 to the 23rd particles. Likewise, moles also relate to mass. Alright, and again, 1 mole equals, I'm just going to call it the molar mass, but probably really it should be atomic mass, but molar mass and atomic mass from the last slide are the same thing. So moles either relate to particles or they relate to mass, and the relationships are different. And in fact, when we get to the gas unit, moles relate to one other thing. They relate to volume. And a mole, 1 mole, of any gas takes up 22.4 liters. But for now, in stoichiometry, we're concerned just with stuff going vertically, so masses relate to moles relate to particles. Alright, so molecular mass, or molecular weight, is the sum of the atomic masses in a molecule. And real quick, molecules are covalent compounds. So things that, two from the right-hand side, 2 nonmetals. So we might have water, carbon dioxide, phosphorus pentafluoride. Our example right here is going to be, I think, sulfur dioxide. But molecules are, again, covalent compounds. So if we have something like sulfur, if we look at the periodic table, has a mass of 32.07. And sulfur dioxide, there's 2 oxygens, so we're going to multiply 16 by 2. And then we're simply going to add 32.07 and 32 and get 64.07. And that is AMUs, which the molar mass is going to be in grams. Likewise, formula mass is the sum of the atomic masses in a formula unit of an ionic compound. So again, molecules are, covalent compounds are made up of molecules. Ionic compounds are made up of formula units. And this is just the smallest entity of an ionic compound. They're big crystal lattices. Here's one right here, sodium chloride. And we'll never find a single sodium with a single chlorine. Alright, instead we'll find billions and billions of sodiums with billions and billions of chlorines, but they'll always be in a 1-to-1 ratio. So sodium are the small things. They've lost an electron, so they're smaller. Our chlorines are the bigger orange things. And again, they come in a 1-to-1 ratio. If we find the sodium in the middle and kind of look to see how many chlorines are around it, we'll just number them. But the sodium in the middle has 1 chlorine, 2, 3, 4, 5, and 6. So it's not sodium chlorine 6 because every chlorine is also surrounded by 6 sodiums. So they're always a 1-to-1 ratio, but we'll never find 1 with 1. So sodium has an atomic mass of 22.99, chlorine of 35.43. We add them together, we have 58.44 AMUs. So that is what a formula unit weighs. But if we wanted a mole's worth, it would weigh 58.44 grams. Alright, our next thing is percent composition. This is just an easy way to find what mass is attributable to what element in a compound. So percent is always part of whole, and we're going to find the percentage of C2H6O. So again, percentage is always part of whole. And if we're talking about compounds, our whole is the compound, or CMPD, and our particle is the element, because elements are parts of compounds. So if we look at our formula, we have the number of moles of elements, and their molar mass divided by the molar mass of our compound. So in this particular example, we have C's, H's, and O's. So we're going to start with C's. So we have 2 of them, and they have a molar mass of 12.011. Our next element that we're looking at is hydrogen. There's 6 of these. They have an atomic mass or molar mass of 1.008. And then finally we have oxygen with an atomic mass of 16. So those are our parts. And now we just need to add up those parts. So 2 times 12 is 24.022. And we're going to add that to 6 times 1.08, which would be 6.048. And add that to 16. And we come up something with 46.070. And that's going to be our whole every time, because that's the molar mass of our compound. So we kind of have 3 different equations, part of whole for carbon, hydrogen, and oxygen. And now I just need to divide these out. And really we're going to multiply by 100. I'm just going to move my decimal place 2 places to the right, alright, instead of actually multiplying it. And we get 52.14% for carbon, 13.13% for hydrogen, and 34.73% for oxygen. And those should all add up to 100. And if they do, you know you've done the problem right. If you get 78%, you know you've done the problem wrong, and you need to go back and change that. So that last one we could probably get from subtracting those first two from 100, but it's probably best to do them all three, just to make sure you add up to 100. And again, percent composition usually is always denoted with 2 decimal places. It's just something that happens in chemistry. If you're not told, you wouldn't know it. But when we have percent composition problems, always round them to 2 decimal places. Don't worry about significant figures. Alright, our next thing is empirical formulas. And empirical formulas are basically working percent composition problems backwards. There is, so in this one, kind of looking at 3 things: potassium, manganese, and oxygen, and we have their percentages. And we want to determine the empirical formula. This is a nice little flow chart, which happens to be in your book. I don't have the page that it's on, but it's there in chapter 3, probably in section 3.5. And our first thing is we need to change really our percentages to masses, which is not on that flow chart. Then we're going to change masses to moles. We're going to mole ratio, and that should give us our empirical formula. So I'm going to put just percentages here on each of these so you know what their unit is. And now we're just going to pretend that we have 100 grams of this thing. Right? Does it matter if we have 100 grams or not? It does not matter, but we're going to pretend that we do. Because if we pretend this, and we have 24.75% potassium, how many grams must we have? Well, if we have 25.75% and we have 100 grams, it must mean that we have 24.75 grams of potassium. Likewise, manganese, we must have 34.77 grams if we have 34.77%. And lastly, we must have 40.51 grams of oxygen. So essentially all we did, we just changed our percentages to masses. Now we need to convert grams to moles. We're going to do that by dividing by the molar mass. Alright, so we're going to set up a few conversions here. Grams is in the top left, so we want grams in the bottom right. And we want to go to moles. Because we are working on molar masses, it's always going to be 1 mole. And 1 mole of potassium weighs 39.10 gram. And for manganese, we have 1 mole. And 1 mole of manganese weighs 54.94 grams. And lastly, oxygen. We have 1 mole, and a mole of oxygen always weighs 16 grams. So we have basically 3 equations, which we just need to divide out. And when we do this, we find that potassium is 0.6330 moles. And you can notice I have 4 significant figures because I have 4 significant figures of grams to start with. Manganese is 0.6329 moles of manganese. And lastly, for oxygen, we have 2.532 moles of oxygen. Alright, so we have gone from mass percentages to moles, and now we need to determine our mole ratio. How do we do that? We're going to divide by our smallest number of moles. So our smallest number of moles happens to be our moles of manganese. So we're going to divide each of our mole amounts by our smallest amount to get a ratio. So 0.6329 and 0.6329 and 0.6329. And again, we have 3 equations. So for potassium, if we divide 0.630 by 0.6329, for manganese, we get 1. For potassium, we're going to get 1 again. And for oxygen, we are going to get 4. And with this, it really tells us that we have 1 mole of potassium for every 1 mole of manganese for every 4 moles of oxygen. So in this case, we have an empirical formula, KMnO4. If it asks you to give me the name, it would be potassium permanganate. If we have 3 elements, it's likely we have a polyatomic ion, and with that oxygen at the end, it's pretty much a dead giveaway that it's a polyatomic ion. And if we have that oxygen at the end, how is it going to end? With an 8 or an ite. All right, our last thing is talking about combustion reactions. All right, and in this one, we're going to want to determine the empirical formula of ethanol. So we have some ethanol in a tube. It's open to air, which kind of has the oxygen flowing through it. And then we have a couple U-tubes with substances that can absorb water or carbon dioxide. So we can weigh those U-tubes before we can react this, then weigh them after, and their weight change tells us how much either carbon dioxide we've collected or how much water we've collected. So again, we want to know the formula of ethanol. This will be easy once you do some organic chemistry, which will happen over Christmas break, but for now you probably don't know what that formula is. But combustion typically is, more often than not, is a hydrocarbon. So in this case, CHO plus oxygen, and that's what combustion always is, reacting something with oxygen. And in this case, if it's a hydrocarbon, we always get carbon dioxide and water. And really what we want to determine is how many C's do we have. So we're going to put X, Y is our number of H's, and Z is our number of O's. So we're really wanting to determine X, Y, and Z for our hydrocarbon. All right, so if we look at this, the carbon dioxide, the carbon from carbon dioxide's got to come from our hydrocarbon. Likewise, the hydrogen from our water has to come from our hydrocarbon. But our oxygen from our carbon dioxide and water can come from just our outside oxygen. So the oxygen is going to be hard to determine, but our carbon, if we know that we collected 22 grams of carbon dioxide, and now if we kind of think back to percent compositions, we can figure out the percent composition of carbon dioxide. How do we do that? Part of whole. So carbon is the part that we want to know. So there's 12.01 grams of carbon in carbon dioxide. So we need to figure out, we need to add basically 2 more oxygens to that. So 32 plus 12.00 equals 44.01. So this little fraction is our percent composition. Alright, so 12.01 grams divided by 44.01 grams is going to give us some ratio of carbon to total. And if we do that math, we're going to find that 6 of those 22 grams, or really with significant figures, 6.00 grams of that 22 grams come from the carbon. Likewise, water, we collected 13.5 grams. And this time we're going to have the same thing, just set up a fraction. So we have 2 hydrogens, so really that's going to be 2.016. And we're going to divide that by 18.016, and that's just our part of whole. And when we do this math, we're going to find that we have 1.51 grams of hydrogen out of that 13.5 grams of water. Alright, again, we just determined that from our percent compositions. So our oxygens are a problem, because we don't know if it's the oxygen from the ethanol or if it's the oxygen from the air. But we know we started with 11.5 grams of ethanol. So if we subtract out the 6 grams and the 1.51 grams, we know that we're left with 3.99 grams of oxygen. And again, that's subtracting 6 grams and 1.51 grams from the 11.5 grams we started with. So now we have 3 gram amounts, and now it's back to a regular empirical formula problem. We need to change our grams to moles, and then divide by our smallest to get our mole ratio. So our molar mass of carbon is 12.011 grams, and that's equal to 1 mole. Likewise, hydrogen, 1.008 grams. It's how much 1 mole of hydrogen weighs. And oxygen is 16 grams to 1 mole. And 3 equations we need to divide out. And 6 divided by 12 is pretty easy. It is 0.5 moles of carbon. And 1.5 divided by 1.008 is 1.499 moles of hydrogen. And 4 divided by 16, or 3.99 divided by 16, is going to be a little less than a quarter, or 0.249 moles of oxygen. And again, we have a mole ratio. It is just not a whole number, so we're going to divide by our smallest mole to get our ratio, which in this case is oxygen, which is 0.249. And half divided by quarter on the top, 0.5 divided by 0.249. Is going to be 2. And obviously our bottom one is 1, because we divided by our smallest. And then 1.5 divided by a quarter is going to end up being basically 6. So if we write our empirical formula, we have 2 moles of carbon for every 6 moles of hydrogen for every 1 mole of oxygen. When we do organic chemistry, we'll find that we really write this C2H5OH, and the OH tells us that it's an alcohol, and ethanol, the ending of that, tells us that it's an alcohol. But notice the molecular formula and the empirical are the same: 2 C's, 6 H's, and 1 O.